So let's continue our lectures. So we talked about this point. So we talked about why says the shortest paths need to be reconstructed in a given environment, but the MST is still maintaining on this. So I believe we are on this slide. So all pairs shortest path. So any question until this point? Yeah. So from coming Monday, we're going to actually meet. Okay, so so we talked about all pair shortest path. What's the all pair shortest path? So building shortest path from everybody. Okay, so notice that the finding the shortest path between a pair of vertices, source and the target, and SMT. So many applications such as the finding center of the diameter of the graph require finding shortest path between all pair of vertices, meaning I want to find the best place to go to everywhere. Something like a logistics center where your packages and parcels are distributed. So mathematicians and computer scientists select the location based on the road condition and where is the best place to install your huge size of inventory store. Okay, so then we can run the Dijkstra algorithm for all cities n times, then solve all shortest path from solve all pairs shortest path problem become n cube. Why? Because you have to run through all the cities, and from that city you need to find all shortest path. Therefore, n cube. Right? Can you do better? You understand this n cube. Let's say you are a CJ Logistic, and you want to build the logistic center. I want to build in here, I want to build in here, build in here, build in here. Why this city? You have to justify. And so you are making real world problem to graph problem, then solve it. The first thing to do is you make a cities to a small sections. Then from small section, and how they connect it. Then cities become your vertex, then road condition become edges, right? Then after making a grid, you are calculating all shortest path from every point to every point. Say from Incheon to everywhere. Then let's say it is Busan to everywhere. Then after calculating everything, then you need to find the best point where it takes the shortest time from everywhere to go to outside, inbound and outbound. Then, oh, okay, this place is my best place. Then the Coupang logistics center will be installed in this place. Okay, so you need to have a justification. So why is the n cube? Because from this point, shortest path is n squared, right? Then you have to run all the cities, therefore multiply by n. So can you do better? Not just n cube. Can you do better? How can you do better? Any idea? So you understand the problem. So now it is the shortest path is n cube. I want to make a better algorithm. How? Kwangmin, any idea?
Very good idea.
Anyone else? How can you solve this problem in a faster way? Say you are learning, CJ, you are learning coupon. Then which place is the best for you? Where you invest your money? And how? Any justifications? Okay, so what is best approach? What's the good approach to solve this problem? So what you're gonna do? Let's say you are a coupon chief operating officer. So what you're gonna do? Maybe if I am a COP, I may use my experience. Experience meaning, based on my previous calculation, that place is better. That place is better. How do you know? And if the new traffic is coming in, meaning new parcels are coming in, just follow that path, which I already computed before. So we called pre-computed, meaning my experience. Right. That is basic of the dynamic program. Dynamic program comes with the 4 basic steps. First one, characterize the structure of the optimal solution and recursively define the value of the optimal solution and compute this recurrence in a bottom-up fashion and extract the optimal solution from computed information using my experience. If it looked like very similar, okay, I know until that point. Then from that point, I'm constructing my optimal point. Okay, so initialization for all shortest path. So make everything is infinite. If I am me is a 0, so I set as a weight. Then there is Floyd-Warshall algorithm. So previously, all shortest path was n cube. Floyd-Warshall can do it much faster, okay, by using experience. Let's do so this is how Floyd-Warshall working. Let's simplify the problem. Let's make A, B, C, D, path 2, path 3, 7, 6, and path 1. Okay, let's solve this. How can I solve this if I'm using n cube, all shortest path? So from A to B, A to C, A to D, I have to compute it. A to B is best place is go to C, go to B. Via C, I can reach with the cost 10. A to C, direct path. Via C, I can get 3. A to D is this path. Via C, I can get a 4. So you are keep repeating to B to A, B to A, B to C, C and D. Okay. So computation, you have to true all component, and this computation is done by checking every path. Therefore, it's n cube. So Do you understand the problem, right? So my problem is I want to find the shortest path for all members to all members. So A to B, A to C, A to D, B to A, B to C, B to D, C to A, C to B, C to D, and T to A, D to B, D to C. The shortest path value. I want to find it. And the computation wise is n cubed. Can you make it better? So let's think about for 2 minutes to warm up your brain. So you understand the problem, right? You given graph. I want to find the all shortest path, all pair shortest path from everybody to everybody in a quick, not just n cube. Okay, not brute force. I want to find it in a quick way. Okay, let's think about for 2 minutes, then we can discuss. Then I'm going to choose, I'm going to ask Roshan and Yejin and Oh Ah-young and Lim Han-min. Okay, so let's think about for 2 minutes.
So I'll start. So what I think is, so for example, if we need to go from A to D, and if we somehow know that the path we need to take also involves C in between, then we don't need to calculate the distance from C to D 2 times. For example, if you already know what the shortest distance is from C to D, then if our path from A to D takes the route via C, then we can know that the path from C to D will be of length 1 or something.
Okay, you are saying you're going to use the sum experience. So starting from A, then can you explain to me step by step?
So let's say the shortest path from A to D is through C and the length is 10, right?
Length is 4, right?
Oh,
length is 4.
Length is 4. Then at the end, when we need to find the shortest path from C to D, we can probably subtract the shortest path from A to D that we already calculated in the top.
Okay.
Something like that.
Okay.
So we minimize the number of calculations by looking up if the calculation has been done before or not.
Ah, okay, great. So Roshan is telling us if there is the C and D is connected and their path is known as the shortest path, then whenever it comes asking, then C is maintaining, okay, me to D is the shortest path is conformed with the 1. Then I don't need to compute this path additionally. Then I can maintain by asking C, right? So every node may maintain the shortest path. Something like, so let's say D to A is a 6, D to A is a 6, okay? But you know what? Okay, this is only path. D to A is a 6, right? Something like this information is stored. It's 10, 7, 9, okay? All right, that is called the conceptually dynamic programming. Okay, dynamic programming meaning you can prune. Prune is you cut the branches. Let's say you are running a tree that from this input, I know what's inside. Therefore, I don't need to compute again. So pruning means if there is one more path and I know it is not working properly, then I don't need to compute all this path. Okay, so by doing pre-computed value, which is my experience, I can do this. Okay, thank you, Roshan. And who else? Oh Ah-young, you may try. No response.
Professor, I have no idea.
Okay, don't worry. Who else?
Yeah, my approach was kind of similar. Oh,
go ahead.
Go ahead.
Janar, you may first.
Oh, okay. My approach was the same as Roshan's. So, so what I would do is that, so first I would start from any like arbitrary point, let's say A, right? let's say A, and then I do like I list all possible paths. Like it's gonna be ACD, ACB.
ACD, ACB. Okay.
Yes, and then if we move to next one, if we move to B, we already know that we can use the adjacency matrix that we built with A, and just use
so,
that and continue building upon it.
So from B is only accessible via A, but this A is already computed.
Yes, so then we can just append the rest, like B, A, C, B,
Okay.
D, A, C, D.
Okay, perfect. All right. So was it Hanmin? No, Hassan, right?
Yeah.
Yeah, go ahead.
So for me, it's not much a technical explanation, but it's more like a life problem explanation.
Okay.
So I think it's similar to Lucian's. So if I'm like a coupon driver and I have experience from delivering the package from A and C, D, and A, I have to come back, right?
Okay.
So I've experienced, I remember all the cycles in the graph. And then whenever next time, if I go to AC, I know that by subtracting AD and CD, I can just get 3.
Okay, good point. All right, thank you. And let's solve this together. So a long time ago, there was a 2 genius called 2, 3, 4, A, B, C, D. A, B, C, D. Bear with me. A, B, C, D. And this path, this path, this path, and this path. This is given 1, 6, 6. This is 7. This is 2. This is 3. Okay. The genius name called Floyd and Warshall. Okay, they invented this mechanism. It's basically you put every node from 2, A, B, C, D, A, B, C, D. So initially, this 0, 0, 0, 0, right? So A to B, can I go to the A to B? In a one adjacent, I cannot. A to C, oh, I can reach via 3. A to D, I cannot, I don't have direct. So set to infinite. B to A, B to O, I can go to there. And B to C and B to D, I cannot, so infinite. So infinite 7, 1, 6, infinite, infinite. Okay, this is my adjacent list. Adjacent list matrix. Meaning with the one hop, I can reach with the value or no. Or no, meaning I'm infinite. Okay, so they thought about, oh, how can I make this matrix problem to dynamic program? Dynamic problem is simply using my experience. Okay, they started with this. This concept is telling if any of the nodes can use A's existence. Okay, A's existence meaning I can use 3, so infinite, I can update 3 and 2, then I update to 5. This one is infinite, I cannot use it. So 6 and 3, then I can use to 9. Do you understand? So concept of this, if I am using A as a relay, can I update higher value to lower value? If so, you can update. Okay, so you may continue. Now I can use B. B is meaning, 7 and 2, I can use 2, 9. 7 and 5, not necessary. And this is it. 9 is only 1. Then I can use C. Then can I update? Okay. Oh, C is not there. C is here. Oh, C is here. So 7 and 3, I can update to 10. Okay, 5 and 1. So 5 and 1, I can update to 6. 3 and 1, I can update to 4. 7 and 9, I can update to 16. 18 is better.
Professor, I have a question.
Yep.
So you update the values that are not in the section, like intersection. For example, in this case, like not in C, rows and columns. So do you update all the values that are infinite values?
Oh, not infinite. Who is a smaller than? Okay, let me check it again. So the concept is this: by using A as a relay, can I update the better route? Meaning higher value will be updated to the lower value, not infinite.
Okay. So you update the values that are not in the same A's and B's and so on.
Yes. So if I'm using C in this case, can I update the value? Okay.
Okay.
Then if I'm running 9 and 7, 10, 4, 6, and 16. Okay, that's pretty much done. Let's go to D. By using D, I can update to 7, 6, and 1. Okay, what else? Nothing else. Then your final result is become 0, 10, 3, 4, 2, 0, 5, 6, 7, 7, 0, 1, 6, 16, 9, 0. Okay, so it is correct answer actually. B, C, D, A, B, C, D, with very simple path, right? So this is basically dynamic programming, meaning if I'm using this guy as a relay, can I solve this? Meaning I have some experience, but can you add this path to the existing path? Okay, let's go back to the slide. So this is called the Floyd-Warshall example. It's well-known DP example. So first, what you need to do for the dynamic programming is you have to characterize the structure of the optimal algorithm, recursively define the optimal solution, and compute the recurrence and extract the optimal solution from computed information. Okay. So Floyd-Warshall's algorithm is running in this way. If you are adding K, and if it creates the shorter path, then I'm updating. Okay, in a given all pair shortest path. It does not work in everywhere, but it only works in all pair shortest path problem. So I understand the input data and I know how to compute the optimal solution, then I can make it faster. How? By using pre-computed result. Okay, so for this case only, the Floyd-Warshall define this path, and it is worked very well, and it is much faster than n cube. Okay, so how to implement it? It's simple. So you are keep choosing the minimum by updating the k. K means, if I'm adding a in the middle, is it shorter? Is it shorter? Then therefore runs in an n cube, but it is not asymptotically no better than a previous Dijkstra. But in reality, I can use the shorter, I can use much simpler matrix computation. Therefore, in reality, it is much faster because I can run it so tight, and I'm using the pre-computed value. Okay, this is the Floyd-Warshall dynamic programming. Okay, you just taste one of the example of the dynamic programming. Okay, let's go back to the new lecture today. So today, we're going to talk about backtracking. So what's the backtracking? So you computed something. Oh, it turns out it is not working. Then go to backtrack. Then from here you solve it. If it is not solution, then go to back point, the last decision point, and you keep continuing. Keep continue. What does it look like? Oh, you look like DFS. And the power of the backtracking is a pruning. Pruning is you can ignore the big part by using your experience. Okay, so remember this comment. So motivation of the minimum spanning tree and shortest path. So prim and Kruskal are the spanning tree, and they are commonly used in the problem connect all the vertices with the cheapest way possible. So something like designing routes between cities. So Dijkstra is a finding cheapest route between two vertices, for example, GPS navigation. You are using the navigation program like a SKT T-map or the Kakao map, something like that. Then the process underlying the Dijkstra algorithm very similar to the Prim's algorithm. Okay? Prim's purpose is to find the minimum spanning tree that connects all nodes in the graph. Dijkstra is concerning only two vertices, which is your source and the target. Prim does not evaluate the total weight of path starting the node, but only individual path. So what I do care is about how long does it take from point A to B. Okay, so remember this. So I just want to comment. Let's start the problem. Do you know the 8 kings problem? So you know the queen in the chess game. Queen can attack diagonal and the horizontally and the vertically and diagonally, which means you cannot position queen here and here. It is illegal because they are attacking each other. You cannot put in here. You cannot put in here, anyone, but you can put in here. Okay. So this is very basic chess. Queen can attack horizontal, vertical, and the diagonal. Okay. Let's say you are given 8 by 8 chess plate. How many queens can you put in a given environment? It's definitely 1, right? But how about 2? By using, it could be 2. How about 3? How about 3? Oh, I can do that. How about 4? I can do that. How about 5? Oh, I think I can do 5. Can I do more? Yes, you can. Something like this, 6, right? By the experience. So let's think about this. How to solve this problem in algorithm way? So your question is, in an 8 by 8 chess plate, how many queen can you put on your chess plate? How many? And how many possibility? And how long does it take your algorithm? Let's think about for 3 minutes. then we can discuss about this. On return, I'm gonna ask whose score is under 1, then PK and Seungju and Ko So-young and Hanmin, Oh-young and Shin Ye-jin. I'm gonna ask you guys sequentially. So you understand the problem, right? Okay, let's think about for 3 minutes, then I will return. Who wants to start? PK? PK, no respond, then Seungjae?
Yes, not sure about it, but so the choices can be so we don't want that queens are at the not in the same horizontal, vertical, or diagonal line. So we just place. If we placed it on 0, 0, then we can maybe place it on the other places that does not meet, each queens are meeting together. So I'm not quite sure about it. Sorry.
Okay, anyone else?
I placed 7, but I couldn't fit the 4th one or the 8th one.
You find the 7? So solution is 8. Yeah, go ahead.
Are we talking about the algorithm or
Algorithm.
the places?
Algorithm. Yeah, by using your algorithm, how many can you find?
Professor, may I try?
Sure. So lady first.
Okay. So first, if you are placing a queen on a specific row, then I would indicate that row first and then go by column. And then if I go by column and find that if that it would be attacked by the original queen, if it's like it'll be placed in the left diagonal of the queen or right diagonal of the queen or below the queen, like straightforward, then I would reject it and then go to the next column and then keep reversing so that I'll be able to know where to place the queen.
Keep reversing meaning keep position the queen.
Yeah, and also and keep moving the column. And if I occupy the queen, then I would indicate the target row again, and then start tracing other columns to find if there are any other places to put the queen.
Okay, so you are saying is, so set this one and keep moving the column, meaning, so you are making the 0.0, then go to the first column and second column and third one, fourth, fifth, sixth, 7, 8, right? Since let's start at 0 to 7. 0 is not working, then you don't compute those. 1, okay, I can do 1. Then in the 1, there is many choices, and I have about 8, right? Then this is not possible, something like this. Is that what you're saying?
Yeah, right. So I would try if it's invalid or valid, the positions, by checking the prior queens, the occupied rows. Okay. Then I'll be able to move on.
What's your computation complexity? What's the computation complexity? Just any guess.
I think it'll be O(n) squared because it has to check and go by column at the same time.
N square. It's not n square because you are picking this one and all possibility. This is n squared, then n square. Then from here, you all possibility. From here, all possibility, right? That n power 8. isn't it?
Yeah, right. Sorry.
Then it is not approachable. That's too complex. Okay, good point. So she's able to solve the problem, but it takes too many computation. So Yongho, you want to try? Thank you, Dajong.
So,
yeah.
For example, if I start from 0.0, then my approach was go to the next row with the closest column, and then use the recursion to keep finding the all possible positions of the queen. And if all position has been covered, then we check if all the numbers of queens are 8 or not. And if it does not reach to 8, then we just return false, which backtracking happens. And we just keep repeat that process until number of queens reaches to 8.
Okay, good point. So he mentioned the backtracking. So how to use the backtracking? So if it is working, you'll keep doing this. If not, you come back to the last decision point, then repeating to next candidate. Okay, Yongho, thank you. This is what you're saying, right?
Yes, right.
Okay, thank you. Anyone else?
Can I try, Professor?
Can I go?
Sure.
First.
Yeah. Go ahead.
Okay. So my algorithm is, so we use a horse movement. So it's like a capital L, letter L. So if the queen was placed on 0, 0, then we have two choices. It's either 2, 1 or 1, 2.
What do you mean 1,
horse
2?
Movement. It's the coordinate.
Okay.
So we can place.
Yeah, it fills up the chessboard.
It's either on the 1, 2 or 2, 1, right? Then we can choose either of those, and then we
1, 2 or 2, 1. Okay.
Yep. We can put the queen over there, and then if we already choose one of the spot, then we mark the other spot as not unchoosable.
Q
and
or
then
Q prime.
Yep, and then all the rows and columns, we mark them as unchoosable as well. And then we go up that way.
Okay.
This one is actually like really fast.
Then I'll find the issue on this. Okay, Adrian, good point. But what if 0.0 is not a good choice? Then you have to repeat this on 0.1. You have to repeat this 0.2, 0.3, 0.7, isn't it?
I think so.
All right. So the good point, very good. But you have to repeat all these 8 candidates. All right. Thank you. Great approach. Anyone else?
Can I go?
Sure.
So the queen starts at 0, 0, right? So let's say
It doesn't need to be. It doesn't need to.
Okay, okay. Just for example, I just choose 0, 0 as a start point. So let's say the column, it looks like a parenthesis R, comma L parenthesis, like a location. So from the 0, 0, we know that all the way that when row equals 0, we cannot actually put the queen, right? And then when L is equal to 0, we cannot put this. So we ignore all the cases.
Okay.
And then we have 0, 0. We compute the differences. So in this case, it's 0, right? So 1, 1, 2, 2, 3, 3 will be ignored as well. And then just pick the same thing and also do the same thing recursively. I pick the next thing and do the same thing recursively. And then eliminating all the same R or L and differences, I think we can make it.
Okay, good point. What's your complexity? So its complexity is like n power of 8 in this case, right? Because you are starting this one and compute this one, all permutation, all possible. then you are moving to this point and you are compute every possibility in here. Moving this point, every possibility. Keep moving to in here, right? Isn't it too complex?
Professor, I have a question.
Yeah.
For the solution that Adrian suggested, and you said the queen might move on, like it's not replaced by 0.0, in the first place. It might not be placed like that. Then what would the time complexity be like?
So you mean Adrian's in complexity?
Yeah.
So if it is not moving, is that what you're saying?
Like, would there be a change to the time complexity if we don't presume that the queen would not be placed in 0.0? Would there be a difference in time complexity for that?
So the most of you talking about at least n cube.
Yeah, right.
So in the worst case, it will increase to some constant. So what I want to tell you today is about backtracking and dynamic programming. I can solve this in a way faster. Okay, let's talk about this. Thank you for your great approaches. And naive algorithm is for each board sequences from 0 to 7, 0 to 7, place a queen there and try to place the rest of the queen. Possible there. And if it's illegal, and unplace the queen. That's the naive algorithm we are doing. Okay, so how large is solution space? Solution space too big because I have to start from 0.0, then 7.7. I start with this position and do all the possibility. I start at position here, all the possibility. Here, and you keep repeating until 7.7. It's too complex. You cannot compute. So better algorithm idea is observation. So we observe that in a working solution, exactly one queen must appear in each row and each column, what we are talking about, right? So if it is positioned there, it is illegal to have, meaning I don't need to compute from the naive algorithm all these consequences. Okay, diagonal also. Redefine a choice to a valid placement and invalid placement. Okay, then how large is it? Then if I started from 0.0, I have to repeat it, this process to 0.1, 0.2, 0.3, 4, 5, 6, 7, right? Because all solution, if we're starting this one as a queen in here, the solution does need to occupy it in here. Queen may start in here. Okay, then because I have a pattern, I have to repeat 0.0 to 7, then I'm repeating. Maybe my best solution starting in here. I have to compute again. Do you understand the problem? So I have knowledge that if I am starting from here at this valid point, then I don't need to compute this guy. But I have to move on to this one. Starting point is this one. Queen position in here, I have to compute. Then maybe the best solution may start in here, meaning I have to compute all the way to here. Okay, let's say your solution runs in n squared, but I have to care about all the cases, therefore, n quad. I don't want to. Can we do faster? Okay, so backtracking using the key idea of the backtracking is abandoning them. We call the pruning. Pruning is cut the tree, cut the branch, maintaining only the main trunk. Okay, so backtracking is find the solution by trying partial solution, then abandoning them if it is not suitable. Then how much big portion can I abandon is the key. Then I can save that computation power. So this is explore the decision. If no more decisions to make, then I can stop. Else, I'm keep choosing, explore. If it is not working, then I go to the last decision point. Then I go to the last point. Then I keep computing. That if the last point is, I saw that point again, meaning I don't need to compute. Okay, so let's practice n queen problem on 4x4. So in a 4x4, I can compute I can place that 4 point. So let's say I position in here, then I cannot do, then I cannot do. Then maybe I can cannot, therefore I can put it here, then I can put it here. Best case is only 3, meaning this is not a best place. Okay, then I'm starting from this point, then this guy, then I can position this guy and this guy. By choosing this guy, I can do in here, then I can do in here. Oh, 4 points. It is a possible solution. How many possible solutions there? So you need to actually compute it. What does it look like? How can you systematically solve this? You know what? I can make a tree out of this. So I can make position 0, 1, 2, 3. By choosing 0, I can make 0, 1, 2, 3. 0 and 0, and you can keep making a tree. Then by choosing 1, you can make 0, 1, 2, 3 position. Meaning, if the subtree pattern appeared again, I can prune them. I don't need to compute. Okay, remember this. I'm going to show you the actual tree. How does a tree look like? Where's my tree? 0, 1, 2. So let me quickly show you. So something like this. I can make permutation tree. Okay, if this pattern appeared again, I don't need to compute. I have experience. If this pattern appeared again in a complex one, this is very simple, only 3 components. I can make 8 components. Then this array is more complex. Then this subsection appeared repeatedly. Then I don't need to compute. Therefore, my computation is height of the tree. Okay, let me go back to the point. So n queen. So we can do this 4x4 on a whiteboard, but 8x8 there's too many possibilities we cannot do on the whiteboard. Then we have to have some systematic algorithm. This is my algorithm and how to solve this. Okay, so basically, row and column is not under the attack from any previous one. Okay, my experience I keep accumulating. So I'm choosing that one, then keep expanding it. Choosing that one, keep expanding. If it is safe, I'm keep adding it. Okay, that's the basic approaches. In the computation complexity wise, it looks complex, but I'm using my experience. Oh, I've been choosing that guy. Then from that point, I don't need to compute all the way to there. Then I can save my computation power. Okay, so this is the solution for possible solution for 8 pins problem. It is known there's only 12 solutions. So by choosing first one, 0.0, you can only find the 2 solutions. Okay, then all these are not choosing 0.0. And meaning you have to compute everything. So computation wise, it's too complex. You cannot compute it in the whiteboard. Okay, then you have to have some approaches, meaning algorithm. All right, so how to pruning it is the key. How to save your computation power? Is it legal or illegal? Meaning, is that the pattern that I faced before or no? If it is faced before, I don't need to compute again. I know that your routine, then I can ignore it. That we called pruning. Then pruning is the key in the backtracking and dynamic programming. Okay, we're gonna talk about this. And n queens problem in a big old n space. And by using this, and this is a continuous n queen problem code. And we can solve this in a Sudoku. Do you know how to solve the Sudoku? Right? So only 1 through 9 is placeable per line and per smaller cube. Then how can you do? We are doing backtracking. What is the backtracking here? So you position one value, and meaning you are choosing this guy. Then by assuming that you will keep moving, possibility, your tree is keep deeper. If it is not, roll back to the last point and make a new point. If not, roll back to the point, making new point. Okay, that's the build a tree, go to deep, and from the last decision point, if it is working, it is keep going. If not, come back to the last point, where your last decision point, then keep continue. Okay, that is the backtracking, meaning, oh, it is working. Not go to the point, to your last decision point. If it's working, okay, keep continue. If not, come back to the last point, come back to the last decision point. Okay, this is what you do. So let's solve Sudoku by using a backtracking. So I know you can solve the Sudoku, but please use the backtracking for this problem. Let's spend 2 minutes and try to solve this Sudoku by using a backtracking. Okay, so let's try to solve this systematically. Let's think about for 2 minutes. How to solve this problem systematically. So I'm going to ask PK, Ko So-young, and Lim Han-min, Hwa-young, Shin-Ye-jin. Any try?
Hello. Professor, can I go?
Sure. Lim Han-min, right?
Yes. So we check which number exists in the box the most first. So in here we have 3 1s and 3 2s, and check where it exists vertically, and put the number where it does not exist.
Oh, wait, start. So which point you are starting? This point or this point, A or B?
I'll start from A.
Okay, you're starting from A. How to solve this?
Yes. So we check the row and column. And in here, we don't have 2 first. So we put 2 in here and put 4 on the last.
Okay.
Yes. And from here, we go to the 4th column. And because the number is almost filled, and we put 3 on the bottom.
3?
Oh, not there, like all the way to the
this
last.
one? Okay.
Yes. Yes. And from here,
so you are solving Sudoku.
So can we do this dynamically?
Yeah. Okay, so you are solving Sudoku. So I want you to solve this systematically. So I understand you, I'm sure you can solve the Sudoku, but how can you make your code systematically approach this? Good point, thank you. And who else?
Can I try, sir?
Sure.
So I'm going to start the point A. As we see the row, the possible number is 4 or 2. So then if I choose 4, and I can only put 2 at the end of the row. And if we see the last column, there's already 2. So we need to roll back to point A. And change it to number 2 instead of 4.
Okay.
And place 4 at the end. And move to next column. And move to next second row. The possible numbers are 3 and 4. So let's put 3 first. And the second column should be 4 then. And move to third law. And the possible number is 4 and 3.
So all of you try to solve the Sudoku.
Can I try, sir?
Sure.
So you start A. You try 1. 1 doesn't work because 1's there. So you try 2. And 2 works. So you go to the next next round. So and then 1 doesn't work, 2 doesn't work, 3 doesn't work. So you put 4 there. And then you go to the second row. 1 doesn't work, 2 doesn't work. And 3 works. So you put 3 there. And then you put.
So I can see that. So I think I gave you the wrong information. So what I meant by then. So I want to 2, 3, 4, 4. Let's make 1, 3, 2, 1, 1, 2, 2, 4. So the main point is I want to use a backtracking and I want to use a dynamic programming. So I know how to solve the Sudoku. Of course, you know how to solve it. Then how do you make it systematically? And how do you train your computer? How can you make your code smart enough? So main approach is from A, B, C, D, E, F, G, H. You are making a tree with a different height. H. So A, there's only 2 possibilities, 2 and 4. So from the root, you can use 2 or 4. By choosing 2 in the B, what's the possibility? I may only use a 4. Okay. Then from here, C, from C, I can use 3 and 4. Right? Then you can keep maintaining, keep expanding your tree. Meaning that if it is illegal, oh, I can find a solution. If it is working, oh, I can find a solution. Okay, by looking at this, oh, this is illegal, meaning I can prune them. If it is illegal, I don't need to compute. Okay, so it turns out I don't need to compute everybody because I can ignore the huge portion. Also, these sub patterns repeatedly appear on these cases. Therefore, oh, that case I already computed, I can ignore. Okay, that's how you solve the Sudoku by using the backtracking. That's what I intended. I'm sorry, I think I was asking, I should ask in a different way. Okay, do you know how to solve it? Do you see how I solve it? So you are making the problem into the simpler graph. Then from the graph, you make a logical precision and decision point. If it is not working, go to the last decision point, keep expanding it. And if you see that decision point again, you already computed before, then I can ignore it. We call the pruning. And by doing this, you can compute, your computation is only the height of the tree. That's how you compute it using a backtrack. Okay, I think I should ask it differently. All right, everybody understand? Okay, can I go? Can I move on? All right. So we know how to solve a Sudoku. I know you can solve a Sudoku, right? Your brain can solve it, human can solve it. My question is, how can you solve it systematically using backtracking? Meaning, how can you solve efficiently? Okay. So this is the Sudoku code I'm making is safe. And if it is unsigned and it's unsigned, this is very, you can make all possible cases. Then in 9 sizes, you can solve this one. Okay, this is not complex. And also you can use backtracking to solve it in a much faster way. So solving Sudoku is by using backtracking. So backtracking is the key to implement exhaustive search problem correctly and efficiently. How can you do? The key is the prune. I saw the pattern before, meaning I can ignore them. I saw the pattern before, I can ignore it. Okay, then you are roll back to the last point, last decision point, and make a new decision. So backtracking is a systematic method to iterate through all possible configuration of a search space. It is a general algorithm which must be customized for each application. And we model our solution as a vector. Then where each element AI is selected from a finite order of set. From the finite set, I just built the tree. Then I'm able to solve that path in a tree. Okay, the finite set as a vector. That's what they mean. Such a vector might be represented as arrangement where AI contains the ith element of the permutation, or the vector might be representing given subset of S, where AI is a true if and only if the ith element of the universe is in an S set. Okay. So idea of the backtracking is after expanding it, we test whether it has so far is a part of the complete solution or no. If it is okay, then I keep expanding it. If not, I can prune them, and by pruning it, I remember if the new pattern, that pattern appears again, I can prune them, which means I'm using my previous experience. Okay, so backtracking in DFS. Oh, you know, it looks so similar to the DFS, isn't it? Okay, so backtracking is just that DFS on an implicit graph of a configuration. So you may think backtracking is application of the DFS. Backtracking can easily be used to iterate through all subset or permutation of the set. And backtracking ensures correctness by enumerating all possibility. For backtracking to be efficient, we must prune dead or redundant branches or search space whether it's possible. Whenever it is possible, meaning whenever I don't need to compute or whenever I have experience on it, I can ignore them. Okay, that's the key of the backtracking. So this is what I prepared today. Any question about today's class, backtracking? So I'm going to, this Wednesday, I'm going to talk about more on the backtracking, and I move on to the dynamic programming. Okay, any question?
I have one question.
Yep. Yep.
So on the what is that, queen thing and the Sudoku, you mentioned the answer is height of tree, right? Does that mean the time complexity of using backtracking is also height of tree?
Okay, so in the view of the big O notation complexity, the backtracking looks very complex. But in reality, why? Because I can prune them. In a given tree, all possible cases, I can ignore those, I can ignore those. Big O computation meaning the while loop. How much computation do I need? How much computation do I need? You know what? It looks very similar to very complex algorithm, but in a backtracking, difference is I can ignore them, I can ignore them, I can ignore them. I can ignore the big chunk, I can ignore the big chunk. Okay. In a big O notation, asymptotic computation, it looks very complex. It's not different from a naive algorithm, but I can ignore some, I can ignore the huge portion, I can ignore the huge portion. That makes a difference. Did I satisfy your question?
So for the queen chessboard, so it's like data n to the 8th.
Yeah, something like this. Very complex.
Okay.
Yeah.
Okay. All right. Thank you.
Thank you. Any question?
Oh, Professor.
Yep.
What was the time complexity that we came upon with like finding the places for 8 queens?
8 queens, the time complexity?
Yeah.
Okay. So time complexity, I may starting from, so this is time complexity for the n queen problem. So I have to run through all the column and position the queen and I keep finding a shape. The shape meaning based on your code, if I've set it is that shape movement or not shape movement, I can store the information. So writing the code in a different way, I'm maintaining my shape position. Then I can make n cube. Why? I'm running every possible row that I'm running on column. Every column, I'm running every row. Then it can return the computation actually could be n squared by maintaining is it safe or no in computation wise, yes. But in the very naive approaches, it looks so complex. I have that position to all the possible, then that position to all the possible. So all 0 to n minus 1 column, then I have to 0 to n minus 1 row, then element is actually 0 to n minus 1 column minus 1, and you keep reducing it. The complexity, if you look at it, complexity it doesn't make sense. That approach is too naive and we don't use it. But how can you make it faster? In approach way, meaning I'm only through 0 to n minus 1 column only by giving as a row as input, and I'm maintaining what is safe. Okay, then we can check, is it safe or no? Is it safe or no? Okay, so don't worry, you can solve this, you can practice one.
I think I can solve it in N.
N? How? How can you solve in an N?
Can you open the like all the possible placements? So you had it in your slide.
Mm.
Yes, so this one. So if you take a look at it, oh, Professor, can I draw, please?
Sure.
So if you take a look at all the possible solutions, you can see that on those two consecutive rows, the index of those two should be larger or equal to 1. Like for example here. So the location of this thing is 0.04. Location of this thing
1.7
is
1.6
1 6.
Yeah.
So the difference between 4 and 6 should be larger or equal than 1.
You can only compute the odd number or even number. That's what you're saying, isn't it? No. Hello, Janar. Okay, I think Janar's connection is lost. So we will talk about this more with the Janar's new approaches, and I have a strong feeling that by looking at a solution, it looks in different way. It looks in different way. Okay, all right. Okay, so we will discuss more